In late 1997, a young physicist from Argentina named Juan Maldacena was working at Harvard. He was not trying to change our view of reality. He was working on string theory. He published a paper. The title was Dense, the Large N Limit of Superconformal Field Theories and Supergravity. It did not make headlines, but inside the world of theoretical physics, it was an earthquake. Maldacena had found a mathematical bridge, a duality. He showed that a complex, curved universe with gravity, a universe like the one we think we live in, could be perfectly described by a much simpler, flatter system of physics without gravity. And this simpler system could live on the boundary, the edge of the more complex universe. It was like finding a Rosetta Stone for the cosmos. The idea was not entirely new. Physicists like Gerard Hooft and Leonard Susskind had been developing something called the holographic principle. They were trying to solve a puzzle about black holes. They had realized that the amount of information you can lose in a black hole seems to be related to its surface area, not its volume. This was weird. It was like the information for a whole room was stored on its walls, not inside the room itself. Maldacena's 1997 paper gave this strange idea a precise mathematical form. It was a concrete example of the holographic principle at work. It suggested our three-dimensional reality might be a projection, a hologram. All the information that makes up you, me, the Earth, the stars, could be encoded on a distant, two-dimensional surface at the edge of the universe. This isn't just a metaphor, it is a mathematical correspondence. It connects everything to information. And the flow of information, the way it changes and degrades, is governed by a single, relentless law. A law that points in one direction. That law is entropy. It is the engine behind the arrow of time. And if our reality is a projection of information, then entropy dictates not just how our coffee gets cold, but the very code of the cosmos. It dictates the fate of everything. Number 18, the universe began in an unlikely state of order. The entire observable universe, all 93 billion light years of it, contains approximately 10 to the power of 80 atoms. The total entropy of the universe today is estimated to be around 10 to the power of 104 in fundamental units. But at the Big Bang, the entropy was staggeringly low, perhaps as low as 10 to the power of 88. That difference, a factor of a quadrillion, is the reason anything happens at all. Everything we see, everything we experience is a consequence of one fundamental fact. The universe began in a state of extremely low entropy. It was highly ordered. This is the most profound mystery in all of physics. The second law of thermodynamics states that the total entropy, or disorder, of a closed system can only increase over time. It never decreases. This law is why your coffee gets cold, it's why your room gets messy, it's why buildings crumble and stars burn out. The universe as a whole is a closed system. So, its entropy must always be increasing. This gives time its direction. The arrow of time points from order to disorder. We remember the past, not the future, because the past had lower entropy. The future is a state of higher entropy. We can, make an egg into an omelet, but we cannot make an omelet into an egg. The process of making the omelet drastically increases the entropy of the egg, breaking down its complex, ordered proteins into a simpler, more disordered state. To reverse that process would require a massive, statistically impossible decrease in entropy. But if the universe is always moving towards greater disorder, it must have started in a state of incredible order. Think of it like a perfectly wound-up clock. The Big Bang wound the clock. For the last 13.8 billion years, that clock has been unwinding. The unwinding is the expansion of the universe, the formation of stars, the evolution of life, the process of your own thoughts. All of these things are temporary pockets of complexity that arise as the universe as a whole moves towards a state of maximum disorder. The puzzle is why the clock was wound so tightly in the first place. Statistically, it is far more likely for a system to be in a high entropy state. If you shake a box of sand with a layer of black sand on top and white sand on the bottom, You will end up with a gray, disordered mixture. You will never, ever shake the box and find the sand has separated back into two perfect layers. The initial state of our universe was like that perfectly separated box of sand. You know, it was a state of immense order and low entropy. This initial low entropy is the ultimate source of all the order and structure we see today. The sun shines because it is a highly ordered ball of hydrogen fusing into less ordered helium, releasing a tremendous amount of energy and increasing the universe's total entropy. A plant grows by taking in that ordered sunlight and using it to build complex ordered molecules, but in the process it releases heat and waste, contributing to the overall increase in cosmic disorder. Every ordered thing, from a galaxy to a snowflake to a line of code, is a temporary structure built by burning through the initial low entropy inheritance of the Big Bang. Without that initial improbable order, the universe would have been a thin, uniform, boring soup of particles from the start. Nothing would have ever happened. There would be no stars, no planets, and no one to wonder why. The fate of everything was set in that first moment, not by a grand design, but by a statistical anomaly that provided the fuel for 13.8 billion years of cosmic evolution. Number 17, your memories are scars left by increasing disorder. The human brain weighs about 3 pounds, but it consumes 20% of the body's oxygen and calories. The process of forming a single long-term memory involves the synthesis of new proteins and the physical restructuring of synapses, a process known as long-term potentiation, which was first discovered in rabbit hippocampi in 1966. This physical change requires a significant expenditure of energy. Every memory you have is a tiny island of order carved out at the cost of increasing the total disorder of the universe. We think of memory as a recording, a clean file stored in the mind, but it is a physical process. And like all physical processes, it is governed by the second law of thermodynamics. To create a memory is to create order. You are taking scattered information from your senses and organizing it into a coherent, structured pattern in your neural network. This is a local decrease in entropy. You are making a small part of the universe more ordered. But the second law is absolute. You cannot create order in one place without creating an even greater amount of disorder somewhere else. The brain pays for memory formation with energy. It burns glucose. This metabolic process is highly inefficient. It takes ordered sugar molecules and breaks them down into disordered carbon dioxide, water, and heat. The increase in entropy from this energy consumption is vastly greater than the decrease in entropy from forming the memory itself. So the net effect on the universe is an increase in disorder. This is why we remember the past and not the future. The arrow of time is the arrow of increasing entropy. The past is the direction of lower entropy. The future is the direction of higher entropy. The act of recording information, of creating a memory, is fundamentally an irreversible process. Leaves a trace, a physical change. You cannot unburn the sugar that was used to power the creation of that memory. You cannot unradiate the heat that your brain produced. The past is fixed because the entropic cost has already been paid. Memories are not perfect recordings. They degrade over time. This is also a consequence of entropy. The complex, ordered neural structures that constitute a memory are subject to the constant jostling of thermal noise and the random decay of biological processes. Maintaining a memory requires constant energy input to fight against this slide into disorder. When that energy is no longer supplied, or when the structures are disrupted, the memory fades. The information is lost, and the system returns to a more disordered, higher entropy state. Forgetting is the default. Remembering is the struggle. Think of it like writing in sand. The act of writing creates an ordered pattern, but the wind and the waves are constantly working to erase it, to return the sand to a smooth, uniform, high entropy state. Your memories are patterns written into the very fabric of your brain, and the universe, through the relentless push of entropy, is always trying to smooth them away. Each memory you hold is a testament to a past battle against chaos, a scar left on your neurology, paid for by burning a small piece of the universe's order. The past exists for you only because you spent energy to record it, leaving a trail of increased disorder in your wake. Number 16, life is a temporary battle against chaos. A single E. coli bacterium contains about 100 trillion atoms organized into incredibly complex structures. Left to itself, this collection of atoms would quickly decay into a simple chemical soup, a state of much higher entropy. To maintain its highly ordered state, that single bacterium must process about 2.5 times its own body weight in nutrients every hour, converting ordered molecules into disordered waste. Life is not a defiance of the second law of thermodynamics. It is the most impressive manifestation of it. Life seems to be an exception to the rule. The second law says everything tends towards disorder, simplicity, and decay. Yet life is about order, complexity, and growth. A seed turns into a tree. A single cell divides and becomes a human being. These are processes of creating immense local order. So how can life exist in a universe governed by entropy? The answer is that life is an open system. The second law applies to closed systems, those that do not exchange energy or matter with their surroundings. But a living organism is not a closed system. It is a whirlpool in the river of entropy. It maintains its shape, its structure, its order by constantly taking in ordered energy from its surroundings and spewing out disordered waste. A plant takes in highly ordered energy in the form of sunlight. It uses this energy to build complex sugar molecules from simple carbon dioxide and water. This is a massive local decrease in entropy. But in the process of photosynthesis and respiration, the plant releases a vast amount of low-quality, disordered energy in the form of heat. The total entropy of the plant plus its surroundings increases, in perfect agreement with the second law. An animal does the same thing. It eats the plant, taking in its ordered molecules. It uses the energy from those molecules to power its muscles, to think, to build its own complex body. But it too radiates heat, exhales carbon dioxide, and excretes waste products. The animal is an engine for converting low entropy food into high entropy waste. It maintains its own internal order at the expense of creating much more disorder in the world around it. But life, then, is a process of creating and maintaining a pocket of low entropy, but it is a temporary and costly battle. The organism must constantly work, constantly consume energy just to stay the same. It is running up a down escalator. As soon as the energy supply stops, the battle is lost. The organism dies. Death is the ultimate victory of the second law. Once an organism dies, it stops taking in energy to maintain its order. The complex molecules of its body begin to break down. The intricate structures of its cells fall apart. Bacteria and fungi, themselves tiny entropy engines, accelerate the process. They consume the ordered tissues of the dead organism and release simple, disordered compounds back into the environment. The body decays, returning its constituent atoms to a simple, high entropy state. The brief, beautiful period of local order is over, so life does not defy entropy. It is driven by it. Life is a strategy for degrading energy. It is a complex and beautiful way for the universe to increase its overall disorder. Every living thing, from the smallest bacterium to the largest whale, is a temporary island of complexity in a cosmos that is inexorably sliding towards a final, simple equilibrium. Number 15, black holes are the ultimate entropy machines. In 1972, Jacob Bekenstein, then a graduate student at Princeton, proposed that a black hole has entropy. He calculated that the entropy is proportional to the area of its event horizon, the point of no return. A single supermassive black hole, like the one at the center of our galaxy, has more entropy than all the stars and gas in the entire Milky Way combined. It is the most entropic object in the universe. Black holes are often seen as cosmic vacuum cleaners, objects of perfect, simple gravity. But in the context of thermodynamics, they are monsters of disorder. When matter falls into a black hole, its information and structure seem to be lost forever. A star is a complex system of particles and energy. An encyclopedia contains a vast amount of ordered information. If you throw them into a black hole, all that complexity and order vanishes. All that is left is the black hole's mass, spin, and charge. This seemed to violate the second law of thermodynamics. It looked like entropy was decreasing, that information was being destroyed. Bekenstein's insight, later confirmed by Stephen Hawking, was that the information is not destroyed. It is encoded on the surface area of the event horizon. The entropy of the black hole increases by an amount proportional to the mass and information that fell in. The total entropy of the universe goes up, as it must. This makes black holes the ultimate end state for matter. They are a state of maximum entropy. Any collection of matter has a certain amount of entropy. But if that matter collapses into a black hole of the same mass, its entropy increases enormously. The black hole represents the most efficient way to pack disorder into a region of space. Stephen Hawking added another twist in 1974. He showed that black holes are not completely black. Due to quantum effects near the event horizon, they slowly radiate away energy, a process now known as Hawking radiation. This radiation is thermal. It is completely random and disordered. It carries away the entropy of the black hole. Over unimaginable timescales, a black hole will evaporate completely, leaving behind nothing but a bath of high-entropy thermal radiation. This process solidifies the black hole's role as an entropy machine. It takes in highly ordered matter and information, processes it, and then slowly releases it back into the universe as the most disordered thing possible, perfectly random heat. It is a one-way street for order. The fate of much of the universe's matter may be to end up inside a black hole. Stars will die and collapse, galaxies will merge, and their central black holes will grow. Over trillions of years, these supermassive black holes may become the dominant objects in the cosmos. And over even longer timescales, googles of years, these black holes themselves will evaporate. They will convert all the complex structures that fell into them, stars, planets, perhaps even the remnants of civilizations, into a final featureless hiss of thermal radiation. The black hole is the logical endpoint of the arrow of time for matter. It is the universe's tool for maximizing disorder. It is a physical manifestation of the second law, showing that even the most extreme objects in the cosmos are slaves to the relentless increase of entropy. The fate of everything that falls in is to be converted into the highest possible state of randomness. Number 14, every decision you make burns a piece of the universe. The human brain operates on about 20 watts of power, the same as a dim light bulb. A single conscious thought involves the firing of millions of neurons, a process that consumes a quantifiable amount of energy derived from glucose. In 1961, Rolf Landauer demonstrated that the erasure of one bit of information in a computational system must, at a minimum, dissipate a specific amount of energy as heat, known as the Landauer limit. This links the abstract concept of information directly to the physical reality of entropy. We often think of free will and decision-making as abstract, non-physical processes. But every choice you make is a physical event happening in your brain. It is a computational process. Your brain takes in information, processes it, and arrives at an output, a decision. This process is not free in the thermodynamic sense. It has a cost. Every decision involves processing information. You weigh options, you access memories, you evaluate potential outcomes. From a computational perspective, this involves changing the state of bits of information in your neural network. Some possibilities are ruled out, uncertainty is reduced. This act of reducing uncertainty, of making a choice, is equivalent to erasing information about the paths not taken. According to Landauer's principle, the erasure of information is a thermodynamically irreversible process. It must be accompanied by an increase in the entropy of the environment. To erase one bit of information, to make a simple yes, no choice definitive, your brain must dissipate a tiny but non-zero amount of energy as heat. This heat is waste, it is disordered energy, it increases the total entropy of the universe. So the act of thinking, of choosing, is an entropy generating process. Your consciousness is an engine that burns the low entropy fuel of the universe, glucose, to produce the ordered state of a decision. And in the process, it exhausts a much larger amount of high entropy waste heat and CO2. The more complex the decision, the more information is processed and the more entropy is generated. This has a profound consequence for our understanding of time and choice. We perceive time as moving forward from a fixed past to an open future. This perception is directly tied to thermodynamics. The past is fixed because the entropic cost of its events has been paid. The decisions have been made, the information erased, the heat dissipated. It is irreversible. The future is open because the choices have not yet been made. The entropic price has not yet been paid. Your sense of free will, the feeling that you are an agent moving into an unwritten future, is a direct experience of the arrow of time. You exist at the boundary between a low entropy past and a higher entropy future. Your life is a continuous process of converting future possibilities into a singular recorded past. And every step of that process, every thought, every decision, contributes to the overall unwinding of the cosmic clock. You are not separate from the laws of physics when you make a choice. You are an embodiment of them. The very act of deliberation is a small-scale thermodynamic process that pushes the universe further along its path toward disorder. The fate of that tiny piece of the universe's order you consumed to make your choice is to become waste heat, radiating away and contributing to the eventual thermal equilibrium of everything. Number 13, the information on your phone is a physical thing that decays. A modern 1 terabyte solid-state drive can store the equivalent of about 500,000 books. This information is stored by trapping electrons in floating gate transistors, a highly ordered physical arrangement. However, due to a quantum mechanical effect called tunnel injection, these electrons will inevitably leak away. A typical consumer SSD left on a shelf without power is estimated to lose its data in as little as 1 to 2 years. The information is not an abstract concept, it is a physical state, and it is subject to decay. We treat digital information as if it were eternal and immaterial. It exists in the cloud. It's just bits and bytes, but all information must be stored on a physical medium. A hard drive stores it in the magnetic orientation of tiny domains. An SSD stores it as trapped electrical charges. A piece of paper stores it as patterns of ink. In every case, information is a specific low entropy arrangement of matter or energy. Because information is a physical state of low entropy, it is constantly under attack from the second law of thermodynamics. The universe trends towards high entropy, towards disorder. A highly ordered arrangement of electrons or magnetic domains is statistically unlikely. Over time, random thermal vibrations and quantum effects will work to erase that order. The trapped electrons will leak, the magnetic domains will flip, the ink will fade, the information will be lost. This process is called data degradation or bit rot. It is a constant battle for anyone trying to preserve information over the long term. Our digital archives, libraries, and server farms must constantly fight against entropy. They do this by spending energy. They use error-correcting codes, which add redundancy to the data. They periodically refresh the data by reading it and writing it again, reinforcing the ordered state. They keep servers in climate-controlled rooms to reduce the rate of thermal decay. All of these measures require a continuous input of energy. The purpose of a data center is to pump out entropy as heat from its cooling systems to protect the low entropy state of the information it stores. When a data center loses power, the battle is temporarily lost, the servers heat up. The rate of decay increases. If the power is not restored, the information will eventually corrupt and disappear. The highly structured data will devolve into a random, meaningless collection of bits, a state of maximum entropy. This reveals a deep connection between information, energy, and time. to preserve information over time, you must expend energy. The more information you want to preserve, and the longer you want to preserve it, the more energy it will cost. Our entire digital civilization, with its vast troves of data, is a massive, energy-intensive project to maintain a state of low informational entropy. It is a temporary dam holding back the river of cosmic decay. The fate of all stored information, if left to itself, is to be erased by the relentless increase of disorder. Every photo on your phone, every document on your computer is a fleeting pattern. Without the constant input of energy to maintain it, it will eventually be lost, its ordered bits dissolving into the random noise of thermal equilibrium. Number 12, civilizations rise by concentrating order and fall when they can't. The Roman Empire at its peak maintained over 80,000 kilometers of paved roads and aqueducts that delivered an estimated 1 million cubic meters of water to the city of Rome each day. These vast infrastructure projects were systems designed to create and maintain social and economic order. Their decay, which began in earnest in the 4th and 5th centuries CE, was a leading indicator of the empire's collapse. The breakdown of these systems represented a massive increase in the entropy of the society. A civilization is a system for creating and maintaining a state of low entropy. It takes disordered natural resources, forests, or wild animals, and transforms them into highly ordered structures, cities, farms, tools, laws, and knowledge. A city is a stunning example of low entropy. It is a highly concentrated, complex arrangement of matter and energy, far from a natural, random state. To build and sustain this order, a civilization must have a source of low entropy energy. Early civilizations ran on the ordered energy of cultivated crops, which captured sunlight. Later, they used wood, then coal, then oil. Each of these is a concentrated low-entropy fuel source. A civilization is an engine that consumes this fuel to build and maintain its complex structures, and in the process, it exhausts a massive amount of high-entropy waste heat, pollution, and garbage. The success of a civilization can be measured by its ability to capture and effectively use energy to combat entropy. The Roman road network allowed for the efficient transport of food and soldiers, reducing the disorder of starvation and rebellion. A modern power grid is a system for distributing low-entropy electrical energy to maintain the order of homes, hospitals, and factories. Laws and institutions are abstract structures designed to reduce social disorder and allow for predictable, ordered interaction. The collapse of a civilization is the second law of thermodynamics reasserting itself on a grand scale. Collapse happens when the cost of maintaining order exceeds the society's ability to pay the energy bill. The historian Joseph Tainter argues that societies collapse under the weight of their own complexity. As a society grows, it must create ever more complex institutions and technologies to solve its problems. Each layer of complexity requires more energy to maintain. The returns on this investment in complexity begin to diminish. Eventually, a point is reached where the society can no longer afford the energy cost of its own structure. A shock to the system, of famine, an invasion, a plague, or climate change can push it over the edge. The systems that maintain order begin to fail. The aqueducts crumble. The roads are not repaired. Trade networks break down. Information is lost. The society fragments into smaller, simpler, more disordered units. This is a rapid increase in social entropy. The complex, ordered civilization decays back towards a simpler, more natural state. The ruins of ancient civilizations are monuments to this process. They are the skeletal remains of low-entropy structures that have been slowly reclaimed by the forces of disorder. We see the same principle at work today. Our global civilization is more complex and more energy-intensive than any in history. Its survival depends entirely on a continuous supply of low-entropy fuel. Its ultimate fate is not a matter of politics or ideology alone, but of thermodynamics. Can we continue to afford the energy cost required to hold back the inevitable tide of entropy? Number 11, the Earth is slowly ironing itself flat. Mount Everest grows taller by about 4 millimeters per year due to tectonic uplift. At the same time, erosion from wind, water, and ice removes rock from its peaks. Over millions of years, erosion will win. The Himalayas, like every mountain range before them, will be worn down into flat plains. This geological process is a slow-motion demonstration of the second law of thermodynamics. The surface of the Earth is a landscape of contrasts. There are high mountains and deep oceans. This is a state of relatively low entropy. Gravity wants to pull everything down to a single, uniform level. A perfectly smooth sphere covered by a uniform layer of water would be a much higher entropy state. The processes of geology are a battle between forces that create order and the relentless force of entropy that seeks to destroy it. The forces that build mountains, like plate tectonics and volcanism, are driven by the Earth's internal heat. This heat is a remnant of the planet's formation and is also generated by the decay of radioactive elements in the core. This is a low entropy energy source. It powers the convection currents in the mantle that move the continental plates, crashing them into each other and pushing up mountain ranges. This is a process of creating local, ordered structures. It takes a flat crust and crumples it into a complex, high-energy state. But as soon as a mountain is formed, entropy goes to work on it. This is the process of erosion. Gravity pulls water and ice downwards. The water carves valleys and wears away rock. Glaciers grind peaks into dust. Wind scours the surface. Chemical reactions in rainwater dissolve minerals. All of these are processes that break down the complex, ordered structure of the mountain and transport its material to a lower, more disordered state. Rocks become pebbles, pebbles become sand, sand becomes silt, which is washed out to sea and settles on the flat, uniform ocean floor. Erosion is the arrow of time written on the face of the planet. It is an irreversible process that always moves from a high-energy, low-entropy state, a mountain, to a low-energy, high-entropy state, a flat plain. It is powered by the sun, which drives the water cycle, and by gravity itself. Over geological time, entropy always wins. The Earth's internal heat engine is slowly running down. As the core cools, tectonic activity will slow and eventually cease. No new mountains will be built. Meanwhile, erosion will continue its patient work. It will wear down the continents, filling in the oceans, the ultimate fate of the Earth's surface, if left to its own devices for billions of years, is to become a smooth, water-covered sphere with no land, no mountains, no features. It will be a state of near maximum geological entropy. Every canyon, every beach, every river delta is a product of this process. They are the evidence of entropy at work, breaking down the temporary order created by the planet's inner fire. The dynamic, varied world we live on is a temporary phase in a long, slow journey towards a simple, flat, and unchanging equilibrium. Number 10, your body is an engine, and death is its final shutdown. The average adult human body contains around 37 trillion cells. Every second, about 25 million of these cells divide, and a similar number die. This constant turnover, known as homeostasis, requires a huge amount of energy to maintain the body's highly ordered state against the forces of decay. Aging is the gradual failure of these maintenance systems. Your body is a thermodynamic engine. It takes in high-grade, low-entropy fuel food and uses it to perform work. This work includes obvious things like moving your muscles, but the vast majority of it is internal. It is the work of maintaining order. Your body builds complex proteins, repairs damaged DNA, pumps ions across cell membranes to create electrical gradients, and replaces worn-out cells. All of these are processes that fight against the natural tendency towards disorder. This fight is called metabolism. It is a controlled burn. You are oxidizing the ordered molecules in your food to release their energy. This process, like any real-world engine, is not perfectly efficient. A great deal of the energy is lost as waste heat. This is why your body is warm. The heat you radiate into the room is the primary sign that you are a living entropy-generating system. You are maintaining your own island of order by increasing the disorder of your environment. Aging is the slow, inevitable breakdown of this engine. It is the accumulation of damage. Over time, the systems that repair the body's components become less efficient. Small errors in DNA replication accumulate. Misfolded proteins clump together. Waste products build up inside cells. This is a gradual increase in the internal entropy of the body. The level of disorder is slowly rising. The effects of this increasing disorder are what we see as the signs of aging. Wrinkles appear as the ordered structure of collagen in the skin breaks down, muscles weaken as cells are not replaced as efficiently, senses dull as neural pathways degrade. The body becomes less able to cope with stress and heal from injury. It is a slow slide from a state of high order and high function to a state of lower order and lower function. Death is the final catastrophic failure of the engine. It occurs when a critical system can no longer be maintained, and the organism as a whole can no longer sustain its fight against entropy. The heart stops pumping blood, cutting off the supply of low-entropy fuel to the cells. The brain stops coordinating the body's functions. The organism ceases to be a coherent, ordered system. After death, the second law takes over completely. The body, no longer powered by metabolism, rapidly succumbs to disorder. The processes of decomposition begin, breaking down the complex, highly ordered molecules of life into simple, disordered, inorganic compounds. The body's temperature drops to match its surroundings, reaching thermal equilibrium. The brief, energetic struggle to maintain order is over. The body's matter and energy are returned to the great, disordered pool of the environment. Life is a temporary loan of order from the universe, and death is the moment the loan is called in. Number 9, the future is probable, but the past is fixed. In quantum mechanics, a particle like an electron does not have a definite position until it is measured. Before the measurement, it exists in a superposition of all possible positions, described by a wave function. The act of measurement collapses this wave function into a single definite outcome. This collapse is an irreversible process. It is the point where a multitude of future possibilities becomes a single, concrete past. The arrow of time feels deeply asymmetric. We have records of the past memories, fossils, historical documents. We have no records of the future. The past feels settled and unchangeable. The future feels open and full of possibilities. This fundamental asymmetry is directly linked to entropy and the nature of information. At the quantum level, the evolution of a system, when left alone, is described by the Schrödinger equation. This equation is time-symmetric. It works just as well forwards as it does backwards. It describes a world of probabilities, the wave function evolving smoothly. There is no inherent arrow of time in this fundamental description. The arrow of time appears when a measurement is made. A measurement is an interaction between a small quantum system and a large macroscopic system, a detector, an eye, a brain. This interaction is thermodynamically irreversible. When the wave function collapses, one specific outcome is realized out of many possibilities. This process creates a record. Information about the system's state is now stored in the macroscopic world. This creation of a record is an entropy-increasing event. To store the information of the measurement's outcome, the macroscopic device must change its state in an irreversible way. This change dissipates heat and increases the overall entropy of the universe. You cannot unmeasure the particle. You cannot erase the record without an even greater thermodynamic cost. This is why we remember the past and not the future. The past is the set of all quantum events that have been irreversibly recorded in the macroscopic world. These records exist because their formation was an entropy-increasing process. The future is the set of all quantum possibilities that have not yet collapsed, that have not yet interacted with the macroscopic world in an irreversible way. The future is probabilistic. The electron could be here, or it could be there. The past is factual. The electron was here, the transition from cooled B to was, is the moment the arrow of time bites. It is a one-way gate. A system moves from a state of quantum superposition, many possibilities, a kind of informational disorder, to a single recorded state one actuality, a kind of informational order. But this local ordering of information is paid for by a much larger increase in thermodynamic disorder in the measuring device and the wider environment. The fixedness of the past is not some abstract philosophical concept. It is a physical consequence of the second law of thermodynamics acting at the quantum to classical boundary. Every event that has ever happened has left a thermodynamic trace, a trail of increased entropy that makes its reversal statistically impossible. The universe is a machine for turning quantum probabilities into a concrete high entropy history. Number 8. A cold cup of coffee explains the end of everything. A hot cup of coffee in a cool room has a temperature of about 90 degrees Celsius. The room might be 20 degrees Celsius. The coffee contains a high concentration of fast-moving, high-energy molecules. The air in the room contains slower-moving, lower-energy molecules. This separation of temperatures is a state of low entropy. It is an ordered state. Over the course of an hour, the coffee will cool to room temperature. This is not a choice, say. It is an inevitability. The cooling of a cup of coffee is the second law of thermodynamics in action in your daily life. It is simple, mundane, and one of the most profound processes in the universe. The hot coffee molecules collide with the cooler air molecules at the surface. In these collisions, the faster coffee molecules transfer some of their kinetic energy to the slower air molecules. The coffee molecules slow down, the coffee cools, and the air molecules speed up, the air warms up slightly. This process continues until the average kinetic energy of the coffee molecules is the same as the average kinetic energy of the air molecules. At this point, they have reached thermal equilibrium. The temperature is uniform throughout the room and the coffee. The energy that was once concentrated in the coffee is now dispersed evenly throughout the whole system. This is a state of maximum entropy for that system. It is a disordered state. The process is irreversible. You will never see a lukewarm cup of coffee in a room spontaneously separate its energy, with the coffee getting hotter and the room getting cooler. While it is not strictly forbidden by the laws of motion, it is theoretically possible for all the air molecules to collide with the coffee molecules in just the right way to transfer energy back into the cup. The statistical probability of this happening is 0 for all practical purposes. There are vastly more ways for the energy to be distributed evenly than for it to be concentrated in the coffee. The universe always moves towards the most probable state, and the most probable state is always the one with the highest entropy. This simple cup of coffee is a model for the ultimate fate of the entire universe. The universe today is like that hot coffee in a cold room. It is full of temperature differences. There are incredibly hot stars and incredibly cold empty space. These temperature gradients are what allow work to be done. They are what power life and all other complex processes. The energy flows from hot to cold, and we build our temporary structures of order in the path of that flow. But this state cannot last. Over trillions upon trillions of years, the stars will burn out. The galaxies will disperse, the black holes will evaporate, all the concentrated energy in the universe will spread out. All the matter will decay into low-energy particles and radiation. Eventually, the entire universe will reach a state of perfect thermal equilibrium. Everything everywhere will be the same temperature, just a fraction of a degree above absolute zero. This is the heat death of the universe. It is the final victory of the second law. In this state, there are no temperature differences, no energy can flow, no work can be done. Nothing can happen. The universe will be a thin, uniform, cold soup of particles. The cosmic clock that was wound at the Big Bang will have completely unwound. The arrow of time will become meaningless because there will be no more change. The fate of everything is to become as boring and unchanging as a cold cup of coffee. Number 7, evolution is not progress, it's just a better way to spread disorder. The biosphere, the sum of all life on Earth, has a biomass of about 550 gigatons of carbon. Each year, through photosynthesis, it captures about 130 terawatts of power from the sun, an amount equivalent to about 6 times the total power consumption of human civilization. This massive energy capture is not for the purpose of advancing or progressing. It is used to drive the molecular machinery of life, a process whose primary thermodynamic output is the conversion of high-quality sunlight into low-quality waste heat, thereby increasing the entropy of the universe. We have a deep-seated bias to view evolution as a ladder of progress leading from simple bacteria up to more complex organisms like ourselves. We see it as a process of improvement, of increasing complexity and sophistication. But from a purely physical perspective, this is a misunderstanding. Evolution is not a drive towards progress. It is a blind, algorithmic process that finds increasingly efficient ways to degrade energy. Life is a chemical system that makes copies of itself. Evolution by natural selection is the simple consequence of this. If you have replication, variation, mutations, and selection, some variants replicate more successfully than others, you will get evolution. It is an algorithm for exploring the space of possible life forms. A successful organism is one that is good at capturing energy and resources from its environment and using them to create copies of itself. A plant that is slightly better at photosynthesis will outcompete its neighbors. A predator that is slightly faster will catch more prey. From a thermodynamic point of view, these fitter organisms are simply more effective channels for the flow of energy. They are better at taking in low entropy energy sunlight, chemical bonds in food, and converting it into high entropy waste heat. The increasing complexity we see over the history of life is not a goal of evolution. It is a side effect of an arms race. A predator evolves better claws, so the prey evolves a thicker shell. This is an increase in complexity, but it is driven by competition, not by an innate drive towards betterness. Often, the simplest organisms are the most successful. Bacteria and archaea have dominated the Earth for nearly 4 billion years and still constitute the vast majority of its biomass. They are incredibly effective at degrading energy. Jeremy England, a physicist at MIT, has proposed a theory called dissipation-driven adaptation. It suggests that random groups of atoms, when driven by an external energy source like the sun, will tend to self-organize into structures that are better at absorbing and dissipating that energy. Life, in this view, is an almost inevitable outcome of physics. It is the best structure that has yet emerged on Earth for the job of turning ordered sunlight into disordered heat. A tree is a more complex and effective entropy-producing machine than a puddle of primordial soup. A mammal, with its warm-blooded metabolism, is a furnace compared to a cold-blooded reptile. Evolution, then, is not a journey towards a noble destination. It is a random walk that stumbles upon ever more elaborate ways to obey the second law of thermodynamics. The fate of any successful lineage is simply to be a better conduit for increasing the universe's chaos. We are not the pinnacle of creation, we are just the most complex energy-degrading system that 4 billion years of random tinkering has produced on this particular planet. Number 6, language itself erodes over time. The English language contains over 170,000 words in current use. However, the average speaker actively uses only about 20,000. All languages are in a constant state of flux. It is estimated that a language, through normal processes of change, will replace about 19% of its core vocabulary every 1,000 years. This constant, gradual change is a form of informational entropy. Language is a system for encoding and transmitting information. It is a highly ordered structure. It has rules of grammar, syntax, and a shared vocabulary. This order allows for complex ideas to be communicated with high fidelity, but like any ordered system, language is subject to the forces of entropy. It is constantly changing, and this change is in many ways a process of simplification and erosion. One of the primary drivers of language change is the principle of least effort. Speakers tend to simplify pronunciation and grammar to make communication more efficient. Complex consonant clusters are reduced. Irregular verbs become regular. Words are shortened. This is a move towards a simpler, less ordered state. For example, the Old English word for head, hifad, became the modern head. The three distinct sounds became one. This is a loss of phonetic information. Sound change is often random and unpredictable. It introduces noise into the system. Over time, these small changes accumulate and dialects diverge. If two groups of speakers are separated, their languages will drift apart, like two copies of a file that are independently corrupted over time. Eventually, they will become mutually unintelligible. The Latin spoken in the Roman Empire eroded and diverged in different ways in different regions, eventually becoming the separate, though related, Romance languages French, Spanish, Italian, Portuguese, and Romanian. The original ordered information of the parent language was degraded into multiple less ordered descendant languages. Words also lose their specific meaning over time, a process called semantic bleaching. The word awesome once meant inspiring terror or dread. Through overuse, its meaning has eroded to simply mean very good. The original, precise information has been lost, replaced by a more general, higher entropy meaning. The very act of transmitting language from one person to another, from one generation to the next, is an imperfect process. Well, children do not learn their native language by memorizing a rule book. They learn it by inference from the noisy, incomplete data they hear around them. Errors and innovations are inevitably introduced in this process. Writing can slow down this process of decay by creating a fixed, low-entropy record. But even written language is not immune. The meaning of words changes even if their spelling does not. And without a continuous cultural effort to maintain literacy and copy texts, the written records themselves are lost to physical decay. The vast majority of the literature of the ancient world has been lost forever. The Library of Alexandria is a famous example of a catastrophic loss of informational order. The language is not a static, perfect system. It is a living, dynamic process constantly battling against the forces of decay and simplification. It is an information system subject to the arrow of time. Its ultimate fate, like all information, is to erode, to lose its structure, and for its message to dissolve into the background noise of a disordered universe. Number 5, the economy is a flow of energy from order to disorder. In 2019, the world's total primary energy supply was about 14,400 million tons of oil equivalent. Nearly all of this energy was used to power the global economy. This energy was derived from low entropy sources, the concentrated chemical energy of fossil fuels, the nuclear energy in uranium, or the kinetic energy of wind and water. The economy's primary physical function is to transform these low entropy resources into high entropy waste. We think of the economy in terms of money, jobs, and growth, but at its physical root, the economy is a thermodynamic system. It is a human-designed extension of the biosphere's project of degrading energy. An economy is a system for taking ordered, low-entropy natural resources and transforming them into goods and services. This transformation process is not efficient. It always produces waste and heat, thereby increasing the total entropy of the planet. A block of iron ore in the ground is a relatively ordered, low-entropy resource. The economy expends a huge amount of energy to mine this ore, transport it, smelt it, and form it into a car. The car is a highly ordered, complex product, a temporary pocket of low entropy. But the process of making it has generated a vastly greater amount of disorder. The fossil fuels burned to power the factories have been converted into dispersed, high-entropy carbon dioxide and heat. The mine has created a disordered landscape. Waste products have been generated at every step. The entire economic process, from resource extraction to manufacturing to consumption, is a one-way flow from low entropy to high entropy. The value we create in the economy is, from a physical perspective, the value of creating temporary, useful structures of order. A house, a computer, a meal all are ordered things that we value, but their existence is paid for by a much larger contribution to the universe's disorder. When we consume a product, we are simply accelerating its journey along the entropic gradient. We eat the food, converting its chemical order into metabolic energy and waste. We use the car, and through friction and combustion, it wears out, rusts, and eventually ends up as a disordered heap of scrap metal. All the ordered products of the economy eventually become garbage and pollution, their atoms return to a disordered state. Economic growth, in its current form, is fundamentally a measure of the rate at which we are converting the planet's low-entropy resources into high-entropy waste. A growing economy is one that is accelerating this process. This is why infinite economic growth on a finite planet is a physical impossibility. The supply of low-entropy resources, fossil fuels, minerals, fertile soil, clean water is finite. The capacity of the planet's systems to absorb the high-entropy waste pollution, greenhouse gases, is also finite. The laws of thermodynamics are the ultimate governors of the economy. Any economic theory that does not account for the flow of energy and the production of entropy is incomplete. The fate of any economic system is tied to its energy sources. When a low-entropy energy source becomes scarce or too costly to obtain, the economy that depends on it must either find a new source or face collapse. The economy is not a perpetual motion machine, it is a temporary engine, and its fuel is the finite stock of order on planet Earth. Number 4. Stars are temporary pockets of order in an emptying void. The Sun is a sphere of gas about 1.4 million kilometers in diameter. It is held together by its own gravity, a force that seeks to collapse it into a state of higher density and disorder. It is held up by the outward pressure from nuclear fusion in its core, a process that converts 4 million tons of matter into energy every second. This delicate balance, which has held for 4.6 billion years, is a temporary stay against gravitational collapse. A star is born from a vast, cold, and relatively disordered cloud of gas and dust. In gravity, the universal force of attraction slowly pulls this cloud together. As the cloud collapses, it fragments into smaller, denser clumps. The gravitational potential energy of the dispersed cloud is converted into heat. The clumps become hotter and denser. This process of gravitational contraction is a decrease in entropy. The system is becoming more ordered, more structured. When the core of one of these clumps becomes hot and dense enough, about 15 million degrees Celsius nuclear fusion begins. This is the moment a star is born. The fusion process, primarily converting hydrogen into helium, releases an immense amount of energy. This energy creates an outward pressure that halts the gravitational collapse. The star enters a long, stable phase of its life called the main sequence. During this phase, the star is a battleground between gravity trying to increase disorder by crushing it, and nuclear fusion creating order by structuring elements and providing the pressure to resist collapse. The star is a magnificent engine for converting the low entropy potential of its fuel into high entropy radiation. It takes highly ordered matter-hydrogen nuclei and fuses it into a slightly less ordered state helium, but in the process it releases a torrent of photons. This light radiates out into the cold, empty space, carrying away a huge amount of entropy. The star maintains its own complex, ordered structure by vastly increasing the entropy of its surroundings. But this process cannot last forever. The star's fuel is finite. When a star like our Sun runs out of hydrogen in its core, the delicate balance is broken. The core will contract and heat up, while the outer layers expand dramatically, turning the Sun into a red giant. Eventually, it will shed these outer layers, and the core will remain as a white dwarf, a dense, cooling ember. More massive stars have a more dramatic fate. They fuse heavier and heavier elements in their cores, creating order in the form of the periodic table. But When they create iron, the process stops. Fusing iron does not release energy, it consumes it. The outward pressure fails, and gravity wins catastrophically. The star's core collapses in seconds, and the outer layers are blasted into space in a supernova explosion. This explosion seeds the galaxy with the heavy elements necessary for planets and life. The remnant of the core becomes either a super-dense neutron star, or, if the star was massive enough, a black hole, the state of maximum entropy. Every star is a temporary structure. It is a fleeting moment of complex order in a universe that is otherwise becoming emptier and more disordered. Stars are the crucibles where the universe's complexity is forged, but they are also the engines that drive its relentless march towards a final, simple, and dark equilibrium. Number 3, the very fabric of reality might be a calculation reaching its end. The Bekenstein bound, a concept from theoretical physics, sets an upper limit on the amount of information, or entropy, that can be contained within a given volume of space with a given amount of energy. This suggests that space itself is not infinitely divisible. There is a smallest possible unit of length, the Planck length, about 1.6 x 10, raised to the power of 35 meters. Below this scale, the concepts of space and time may not even exist. Reality might be fundamentally digital. The idea that the universe is a kind of computer is not new, but modern physics, particularly the holographic principle and theories of quantum gravity, gives it a new and startling plausibility. If reality is made of information, of bits, then the laws of physics are the algorithm that processes those bits. The passage of time is the running of the computation. In this view, the state of the universe at any given moment is a vast collection of information. The Big Bang was the initial input, the program's starting condition. The evolution of the universe since then is the step-by-step execution of the cosmic code. Every interaction between particles is a small step in this computation. Entropy and the arrow of time fit naturally into this picture. A computation is an inherently irreversible process. You start with a simple, ordered input the program and its initial data and run it to get a complex, often unpredictable output. The process of computation, like any physical process, must obey the second law of thermodynamics. It consumes energy and generates waste heat. The logical irreversibility of the computation, you can't easily run it backwards from the output to find the unique input, is mirrored by the thermodynamic irreversibility of the physical computer. The increasing entropy of the universe can be seen as the universe computing its own future. The initial low-entropy state of the Big Bang was a highly compressed, simple set of instructions. The unfolding of the cosmos, the formation of galaxies, stars, and life, is the result of that program running, generating complexity and, as a byproduct, increasing the overall disorder. The universe is like a compressed data file, a zip file that is decompressing itself. The uncompressed file is much larger and appears more complex, but the total information content was all there in the beginning. The process of unzipping it is the arrow of time. This leads to a chilling thought about the ultimate fate of everything. If the universe is a computation, does it have an end? A computation can halt. It can reach a final state from which no further operations are possible. The heat death of the universe, the state of maximum entropy, looks very much like a computational halt. It is a simple, repetitive, unchanging state. The cosmic program has finished running. The final output has been reached. Our reality in this framework is a temporary phase. It is the dynamic, interesting part of the calculation. The intricate dance of particles and forces we observe as the universe processing information. But this processing is finite. The amount of information is finite as suggested by the Bekenstein bound, and the number of computational steps may also be finite. The fate of everything is to be the final line of output from a 13.8 billion year-long calculation, a result that, once printed, will remain static for eternity. Number 2, the ultimate fate of the universe is cold, dark, and simple. The current temperature of the cosmic microwave background radiation, the leftover heat from the Big Bang, is 2.725 Kelvin. Due to the expansion of the universe, this temperature is constantly dropping. In 100 trillion years, the last stars will have faded. In a Google 10 to the power of 100 years, the supermassive black holes at the centers of galaxies will have evaporated. The universe will be almost perfectly empty, cold, and dark. The story of the universe, as dictated by entropy, has a clear beginning, a middle, and an end. The beginning was the Big Bang, a state of incredibly low entropy. The middle is the present era, the stelliferous age, where stars shine and the universe is filled with complex structures. This is a temporary, vibrant phase driven by the unwinding of that initial order. The end, however, is the long, slow return to simplicity. This future can be broken down into a series of epochs. First, the stars will die. In about 100 trillion years, all star formation will have ceased, as the free gas needed to form them will be exhausted. The smallest, longest-lived red dwarf stars will finally burn out, and the universe will go dark. The only remaining objects will be the corpses of stars, white dwarfs, neutron stars, and black holes, along with wandering planets. This begins the degenerate era. Over unimaginable timescales, the orbits of these dead stars and planets will decay due to gravitational radiation. The galaxy's contents will slowly spiral towards the central supermassive black hole. Occasionally, two brown dwarfs or white dwarfs might collide, producing a brief final supernova in the darkness. But even these remnants are not eternal. Protons themselves may be unstable. According to some theories, protons have a staggeringly long but finite half-life. Over timescales of 10 to the power of 40 years or more, all matter as we know it, the white dwarfs, the neutron stars, the planets, will dissolve into a thin gas of lightweight particles and radiation. The only large-scale structures left will be the black holes. This is the black hole era. For a time, black holes will be the only organized matter in the universe, but they are not permanent either. As Stephen Hawking discovered, black holes evaporate. They slowly radiate away their mass as a faint cold thermal glow. This process is incredibly slow. A solar mass black hole would take 10 to the power of 67 years to disappear. The supermassive black holes in galactic centers could last for a Google years. Finally, after the last black hole has evaporated, the universe enters its final state, the dark era. It will be a vast, empty, and cold void filled only with a diffuse, near-zero energy bath of photons, neutrinos, and a few stray electrons and positrons. The universe will have reached a state of maximum entropy. It will be in perfect thermal equilibrium. Time itself will lose all meaning, as there will be no change, no processes, no events. This is the heat death. It is not a fiery end, but a slow, cold fading into nothingness. It is the ultimate consequence of the second law of thermodynamics. Every structure, every particle, every flicker of complexity is temporary. The fate of everything is to be diluted and dispersed into a featureless, eternal equilibrium. The brief, brilliant flash of cosmic history that we are a part of will be over, its order completely spent, its story concluded in a final state of perfect, simple, and everlasting silence. Number 1. Your existence is statistically impossible, yet here you are. The cosmological constant, the energy of empty space itself, is incredibly small. If it were significantly larger, the universe would have expanded so rapidly that no galaxies or stars could have formed. If it were negative and large, the universe would have collapsed back on itself moments after the Big Bang. The observed value is about 120 orders of magnitude smaller than predicted by quantum field theory. This is the most severe fine-tuning problem in all of physics. We are left with a paradox. The fundamental laws of the universe seem to demand a final state of simple high-entropy chaos. The arrow of time, driven by the second law of thermodynamics, points relentlessly towards this heat death. And yet, here we are. We exist in a universe that is not only capable of forming complex structures, but seems to be exquisitely fine-tuned to allow for them. The initial conditions of the Big Bang were a state of astronomically low entropy. The values of the fundamental constants of nature, the strength of gravity, the mass of the electron, the energy of empty space, are all set to values that fall within an incredibly narrow range that permits the existence of stars, planets, chemistry, and life. If you were to change any of these constants by a tiny fraction, the universe would have been sterile and dead. This is the anthropic principle. It notes that the universe we observe must, by necessity, be one that allows for the existence of observers. There are two main ways to interpret this. The weak version simply states that our location in time and space is privileged in the sense that it must be compatible with our existence. We find ourselves living in the stelliferous era on a life-bearing planet, because we couldn't exist in the early plasma of the Big Bang or in the cold void of the heat death. The strong version is more controversial. It suggests that the universe is somehow compelled to have the properties that allow life to arise. Some take this as evidence of a designer. Others turn to the idea of a multiverse. If there are an infinite number of universes, each with a random set of physical constants, then it is no surprise that we find ourselves in one of the very rare ones, where the numbers happen to be right for us. We won the cosmic lottery, but there were an infinite number of tickets. Regardless of the explanation, our existence is a profound statistical anomaly. We are the products of a universe that started in an impossibly ordered state and is governed by laws that are perfectly balanced on a knife's edge. We are temporary complex structures, tiny eddies of low entropy, in a cosmic river that is flowing towards a vast sea of disorder. The fate of everything is to dissolve into this sea, but the fact that we are here at all, to observe the river, to understand the laws that govern its flow, and to contemplate its final destination is the most remarkable thing of all. We are the universe's way of briefly knowing itself, a fleeting moment of consciousness, paid for by the unwinding of the cosmos. The entropy that will ultimately erase everything is the same force that drove the formation of the stars, that forged our atoms, and powers the metabolism in our brains that allows us to wonder. We are living proof that even in a universe doomed to disorder, incredible, improbable, and beautiful things can happen along the way.